Hey everybody, sorry it's a little bit late starting. I've had a bit of an issue with the room that I normally do this in, so I've had to move everything downstairs, and I've left my headphones upstairs, so I'm going to have to run upstairs and get those. So give me a second please, I'll be back in a minute. Right, I'm back. Just looking at the chat. Happy birthday, Laura. And I finally know Crazy's real name, so that's good to know. Right, I'm just plugging my microphone in. Can somebody put in the chat whether or not this microphone's okay, please? I know it'll take a little time for the delay to work its way through, but I think this microphone might be better because it's got a longer cable. So I'll just keep talking, shall I? It's fine, great, okay, fine, that's good. Do I sound like a robot? Remember on Wednesday you were saying I sounded like a robot. I listened to it back and it didn't sound very good. Okay, so we are doing the second part of the rates of reaction booklet. Okay, so we're up to the page that's on the screen now, concentration time graphs. So remember, I think I said on Wednesday that I wasn't sure how well this would go, given the fact that normally would draw the graphs in lessons and things like that. So I've got my completed notes as well to show you any graphs that have been drawn. I mean, hopefully you've managed to draw the graphs yourselves, and we can we can talk through your graph, if you know what I mean, if it's there on the notes. Right, okay, let's get started then. So concentration time graphs first of all. So we can obtain a concentration time graph by continuously monitoring an aspect that changes over the course of the reaction. So basically what that means is you set a reaction going, and then at regular intervals basically, so it could be every minute, every 30 seconds, you record or you measure an aspect of the reaction that could change over time, okay? And then you would plot that as what's technically called a concentration time graph, okay? So obviously you could measure the concentration. What else could you measure? So these are examples of things you could measure or monitor over time. Volume of gas, if the reaction produces a gas, obviously. And obviously if the reaction makes a gas, it's going to get lighter because the gas is going to escape, so you could monitor the loss in mass. So sometimes questions ask you, they'll present you with a concentration time graph, and they might say, how else could the student have followed the rate of this reaction? So that's kind of what they're after there. pH and colour. If one of the reactants or one of the products has colour, you could monitor the colour, and we'll look at that in a second on how you actually do this sort of colorimetry technique. Okay. So you would end up, let's say for argument's sake, you were monitoring the concentration, obviously in moles per decimeter cubed over time, you would end up with a graph that looks a bit like that. So how would you then calculate the rate at any point of that, that reaction? You would calculate the gradient. Okay, so I'm going to switch to my completed notes now. So it's exactly the same graph. Okay, so there it is there. So you can see there's two lines, or there's two tangents drawn to the curve. The blue one is the initial rate. So that's the rate at the very start of the reaction, okay, when time equals 0, okay. So you know all those things, those tables we were looking at the start of, or in the middle of Wednesday's lesson, those initial rates results. So that's the rate at the start of the reaction, okay. So you can see that tangent is being drawn, so it hits the curve at time equals 0. So there, okay. The green tangent is drawn, and so basically what that's doing is that's hitting the curve there. So basically what that green tangent showing is the rate at that point there, okay? So sometimes you're asked to calculate the initial rate, so you would draw the tangent so it hits the curve here, or you might be asked to calculate the rate at a particular time in the reaction, okay? And that's what you do there. So the most common mistake I would see is if somebody was working out the rate of reaction for that point there, the most common mistake I see is a student would read off the y value, okay, so they would draw a line straight across to y-axis and get a value for that, okay, and they would divide that by whatever the time is at that point, okay. So that's not the way to calculate rate, because that's not the gradient of that line. So what you need to do is calculate the change in y, okay? So you need to calculate the change in y. So let's do it for the initial rate. And you need to calculate the change in x, okay? And then obviously the rate is equal to the change in y, the change in concentration, divided by the change in x, which is the change in time, okay? So that's how you would calculate the rate at any point in a graph like that. So how big the range in the mark schemes for working out gradients of tangents? There is a range. I don't know the exact range. Sometimes they would say within plus or minus 10% of what the exam board deems is the correct value. So yeah, tangents are very variable. It all depends on where you sort of hit the curve, but obviously you've got to be within the range, okay? So try and perfect your tangent drawing, I suppose is what I would say there, okay? Right, so back to the notes then. So just a few blanks to fill in here. So the graph, this graph shows that the rate at the very start of the reaction is high, and that's due to obviously the tangent's very steep at that point, so that's telling you the rate's high. But why is the rate high at that point? That's due to the concentration of the reactants being at their highest, and therefore there are the greatest number of collisions, there should be an S there, sorry, collisions with energy equal to or greater than the activation energy per second. Okay, remember, rate is all about collision frequency, the number of successful collisions, the number of collisions with energy greater than or equal to the activation energy per second. That's the rate aspect, okay? And as time proceeds, you can see that the rate decreases, okay? So, you know, the tangent is very steep at the start, it's getting less steep, it's it's getting less steep, and eventually the gradient of the tangent would be 0 because there's no change in the y value. The concentration's not changing anymore. Okay. Okay, right. So one of those factors, sorry, I'm scrolling back up here. One of those factors was colour. So what we're going to look at now very quickly is how you would monitor rate by a technique called colorimetry. Okay, so my students haven't done this yet. Obviously, it's something that we would do when we get back to college. So let's just go through this technique here. So not all chemical reactions produce gases. That's fairly obvious, isn't it? If a reaction involves a colour change, this can be continuously monitored. So remember, throughout the reaction, this can be continuously monitored at regular intervals, and you can therefore obtain the rate of the reaction through that. The process is carried out using what's called a colorimeter. Okay, so I'll just quickly explain this process. So we're going to label this up a little bit. So what we've got here is a light source. So this is just a very crude diagram drawn by me. Light source. Okay, so it's basically just a bulb. It passes through a filter. You don't need to know the reasons for this the filter, by the way. The reaction is obviously in this test tube here, and I've coloured it in like a yellowy orange colour, because it's going to represent something like iodine. Reaction is there. We've got a detector on the other side of the reaction test tube, and this 1, 2, 3 is just an arbitrary number I've put in there, and this is the absorbance reading. How much of the original light source has been absorbed by the reaction vessel. Absorbance. Okay. And basically, the darker this is, so the higher the concentration, in other words, of the substance that has colour that's in there, the more will be absorbed, more light will be absorbed. Okay, so we'll just write that in there. The darker the colour, the more light is absorbed, and obviously less passes to the detector as a result. So if we use this reaction between, this is propanone, CH3COCH3, and iodine, so what's going to happen as the reaction proceeds? Is this a required practical? You could be asked to describe how a student could perform this reaction. So yes, you could be asked to do this, okay? To talk about this, to write about this. So you may not have done this yet, Laura, okay? So maybe it's not familiar with you. So if that's the case, don't worry about it. I'm sure you'll do it when you get back to college. But because it's in my notes pack, I'm going to cover it now, if that's okay. As the reaction proceeds, the orangey brown colour of iodine fades. Obviously, this reading here will change, won't it? Okay, so the light goes through the filter, it passes through this reaction vessel. So as the reaction takes place, this is going to get lighter and lighter, which means that less will be absorbed by this reaction, more will hit the detector, and this value here is just going to change. Okay, so don't worry too much about these numbers here. Okay, it's more about this next bit really. So how would you then I suppose, Laura, this is going to answer your question. What would you write if you were asked to describe the procedure? So what you would do is you'd prepare standard solutions, so that's solutions of known concentration of the chemical that has the colour, so iodine in this case. Okay, so you might make 1 mole per decimeter cubed, you might make 0.75 moles per decimeter cubed, you might make 0.5 moles per decimeter cubed, 0.25 moles per decimeter cubed, and obviously you wouldn't bother with 0 moles per decimeter cubed, but you would run something with no concentration, so you'd have a test of like a standard of water. Okay, so there it says there, run a test using distilled water to 0 the colorimeter. So that's giving you the absorbance, the maximum absorbance reading. Okay, when there's nothing's absorbed, everything gets through the colorimeter. And then number 3, measure the absorbances for the different standard solutions. So what that's going to do is it's going to tell you when the concentration is 1 mole per decimeter cubed, this is the absorbance reading. When it's half a mole per decimeter cubed, this is the absorbance reading, and so on. So you build up basically this linear relationship here. Okay, so when the concentration is this, the absorbance is this. When the concentration is this, the absorbance is this, and so on. Okay, you would then carry out the reaction and you would take absorbance readings at regular intervals. Okay, and then what you would do is once you know the absorbance reading at your regular intervals, you can read off your calibration curve. So for example, let's say after 1 minute the absorbance was, let's say, right up here. Okay, so that's telling you that the concentration after a minute was there. Okay, see how it works? And then after 2 minutes, absorbance goes down because the colour's fading. You get that. So the concentration would be that. You go to that, 4 minutes, that, and so on. Okay? So this calibration curve is able to tell you what the actual concentrations are from the standard readings that you've already taken. Okay? So that's basically that little experiment there. So hopefully you'll get a chance to do this at college when you go back. I've made a PAG video on this, so if you wanted to check out my playlist on the PAGs, it's in there. Okay, so how can we use concentration time graphs to determine orders? That's the next little bit. So I haven't been very original on how I've sort of laid these out. So the rate of reaction can be calculated at any point on a concentration time graph by calculating the gradient at that point. The order can also be determined from the shapes of the graphs. So the first graph you've got is a 0 order. Okay, so how could we justify if we were asked to explain why we're saying that 0 order? So what could we say? Well, we've just learnt that a concentration time graph, the gradient shows us the rate of the reaction. Okay, so this straight line graph has a constant gradient. So what that means is, as the concentration's changing, the gradient isn't changing. So in other words, the rate isn't changing. So the rate is constant for that one. Okay, so just put in there gradient constant. Okay, so the next one is a first order reaction. And we're going to do a bit more on first order reactions in the second half of this page. So if you notice for this graph, okay, the rate is changing because the gradient, the slope of the gradient, of the tangent, sorry, is changing. So the rate is changing with concentration. So it's definitely not 0 order, okay. So we'll say gradient changes. It changes in a special way, and you'll see in a second what that is. Rate changes, gradient changes, rate changes. Okay, And then this is a second order graph. So you can see again the rates changing with concentration. So you've got a very steep, so it's a very high rate, but very rapidly the rate is changing much more rapidly with this one. Okay, so we'll just get that on there. Gradient changing. The rate changes more rapidly. Okay. Right, so more about the first order reaction. So you can see there this little part of the notes is saying half-life, T1/2, and first order reactions. Okay, so half-life is the time taken for the concentration of a reactant to decrease by half of the value, okay, that it was at. So first order reactions have got this special sort of feature in the fact that they've got constant half-lives. Okay, so it's exponential decay. So this graph, going back to this graph here, that's showing exponential decay. Okay, and that's how you can tell that that's first order. The reason it's doing that is because the half-life of the reaction is constant. So every so many, whatever the half-life is, let's say it's x seconds, every x seconds the concentration halves. Okay, keeps half in every x seconds, which you can see on this graph here. Okay, so what have I got written there? So half-life is the time taken for concentration to decrease by half. That sometimes gets asked, by the way, to define half-life. First order reactions have a constant half-life. It's worth highlighting, where the concentration of the substance continues to halve over the same time period. This is known as exponential decay. So we can see from a concentration time graph if a reaction is first order by measuring successive half-lives and seeing if they are the same or almost the same. So when you start answering exam questions, you might find that the half-lives kind of slightly differ, maybe by 5 seconds, 10 seconds, something like that. If they're roughly the same, then you can say that it's a first order reaction. Okay, so you can see here, let's just write something on the graph here. This graph shows a constant half-life so hopefully you can see the half-life. So to go from 0.1 to 0.5, the period of time is taken is 100 seconds. Okay, to go from 0.05 sorry, to 0.025 has taken another 100 seconds, and then to go down half again, it's taken another 100 seconds and another 100 seconds. Okay, so 100 seconds. Therefore, first order, for that reactant. So what I would be telling my students, and I know some of my students are in the room now watching this, so this is directed definitely to you guys, okay, because obviously this is your lesson on this. If you have a concentration time graph in a question, the first thing you should do is look at the half-lives, okay? And the chances are you've been given that graph to establish that it's first order. Okay. Sorry, x-axis not visible. Okay. Okay, so the next little part of the note is how you can calculate the rate constant K from a concentration time graph. Now obviously this is effectively my lesson with my students on this, so if I'd been in college with them, I would have spent some time in the lesson getting them to draw this graph here. Okay, now you may or may not have graph paper at home, so I'm going to show you the graph that I've drawn on that. Okay, so let's just read through the question and then I'll show you the graph and we'll look at how you do the calculation. So when heated strongly, nitrous oxide decomposes into its elements according to the equation below. So we've got an equation there, this one here. The concentration of N2O was recorded every 50 seconds and the results of the table in the table were obtained. So we've got concentration of N2O gas against time. So obviously we can plot a concentration time graph. So let's have a look at the graph that I got for this one. So I need to scroll all the way at the bottom, sorry, where all my graphs are. Okay, make that a bit smaller. Okay, so there's the graph from that I got from that. Okay, so obviously if that was an exam question, you would be marked on how well you've plotted your points. Have you remembered to label your axes? You wouldn't believe how many students lose marks because they just don't label axes and things like that. So obviously remember to label your axes correctly. This one is labelled, but it's off the screen. Concentration in moles per decimeter cubes up there. Okay. You would then draw a nice smooth curve through the points. Okay. And then let's have a look at the questions. So we've done A, plotted a graph of N2O against time. Use your graph to determine the order of reaction with respect to N2O. So like I've just said, if you've got a concentration time graph, look at the half-lives. Okay, so you can see I've already done it here. So to go from 1 mole per decimeter cube to 0.5 has taken 50 seconds. To then go down to 0.25, so from there to there is another 50 seconds. To go from there down to there, which is another half-life, has taken another 50 seconds. If you can, try and get 3 half-lives drawn, and then you can say, right, the half-life is constant, and quote the half-life 50 seconds in this case, and then you can say it's first order with respect to that reactant. Okay, so let's just fill that in now. So we've plotted the graph of rate against time. Okay, so that's done. Use your graph to determine the order. So what would you write there? You could say it's first order. And the reason for that is constant half-life. Sorry, I haven't left a massive amount of room for all of this. Constant half-life. So you could just say first 3 half-lives, I'll just put T a half just to save a bit of room, is 50 seconds. So you would demonstrate that you've done that. Determine the rate when T is 70 seconds. So we've got to calculate the rate. So how do you calculate the rate? You draw a tangent to the curve and where it hits the graph at 70 seconds. Kind of, yeah, you can. Yeah, I hadn't spotted that. Good spot. But they wouldn't make it as obvious that obviously in an exam. I'm going to have to change these notes now and make the results a little bit less obvious. But yeah, good spot. Good spot. But no, if they're going to get you to draw a graph, they're going to want you to calculate half-lives. You wouldn't get any marks without doing it on the graph. And they normally say in the questions, show you're working on the graph. Okay. Right, the rate at 70 seconds, so you can see I've drawn a tangent to the curve, so there it is there. Change in y divided by the change in x has given me a rate of around about 5.28 times 10 to the minus 3 moles per decimeter cubed per second. Just out of interest, did anybody... Oh, Jake, I think that's a risky strategy. If like I've just said before, if they're getting you to draw a graph, they're going to want you to do what I've shown you there, okay? I think basing it on units alone is a risky strategy. Like I've said a few times, I'm not a marker for exam boards, so I can't tell you sort of definitively whether you could get away with that, but that seems to me a little bit of a risky strategy, in my opinion anyway. I certainly won't be advising my students to go down that route. Okay, I'll be wanting them to draw the graph and talk about how the graph shows that it's first order rather than the units. Okay, if you want to do that, you can. I certainly wouldn't advise it, but it's your call. Okay. Just out of interest, did anybody actually get to draw the graph for this? I'm interested to see if anybody's got a rate calculated from their own graph. Don't worry if you haven't. I'm just interested to see how yours compares with mine. That's all. Because somebody asked about the range allowed kind of thing. I reckon the answer is going to be no. Who's got graph paper at home? Just give a little bit of time for the chat to keep to catch up. Doesn't look like it. Okay. Okay. Right, let's go on with this then. So that's fine, don't worry. I just thought I'd ask. Right, so shall I determine the rate when t equals 70 seconds? I'll just put my answer in, shall I? So I got 5.28 times 10 to the minus 3 moles per decimeter cubed per second. Whatever you do, don't forget your units. Mol dm minus 3 s minus 1. Okay? So then it's saying determine the rate, use your results to part C to calculate a value for the rate constant K. Right, so what have we established so far? We've established that it's first order with respect to N2O. N2O is the only reactant in this reaction, so therefore the rate equation is rate equals K N2O concentration raised to the power 1, or you can put the 1 in or leave it out, it's fine, whatever. Therefore K equals rate over N2O concentration. Okay, we've just been asked in part C to calculate the rate at 70 seconds, so that's obviously been, you've got to do that to help you with this part of the question. So I'm going to use that rate at 70 seconds, 5.28 times 10 to the minus 3, that's my rate, and the concentration of N2O at 70 seconds, obviously you would get that from the graph, wouldn't you? So you'd find your 70 seconds, these graphs are awful to read, aren't they? You'd read off the concentration value of the, whoops, that's not, I wanted the laser pointer. So it's here, I think. That'll be why that mark's there. Anyway, I've worked it out already. I got the concentration to be 0.38 moles per decimeter cubed. Okay, so that's the concentration value for that point. It doesn't look like we're going to finish it. I think we're going to have to leave the Arrhenius stuff till next week by the looks of it. And then, so I got for this, sorry, this is very messy, 0.0139 seconds to the -1. Okay. And again, there's going to be a range allowed for that because the rate was based on a gradient that we've calculated, so that's going to vary a little bit. Okay. There shouldn't be any variation in the concentration. Okay, so that's what I got for that. Okay. Right, next little thing, calculating the rate constant K from the half-life. So this can only be done with first order reactions, by the way. Okay, so for first order reactions, a much easier and much more accurate way to calculate the rate constant. So why is it more accurate? It's more accurate because tangents, so that little star there is obviously linking to that. Tangents are, I've just got on my notes here, 2 variable. So tangents are 2 variable. So a more accurate way, if you know what the half-life is, basically you can just plug it into this equation. Okay, so K equals ln 2, so that's the natural log of 2 divided by T1/2, half-life. Okay, so that's an equation that you're going to need to memorize because it's not on the data sheet. Okay, so if we do it that way, we're going to get K equals the natural log of 2 divided by, and we said the half-life was 50, didn't we? So when you put that into your calculator, you get 0.0139, which is actually the same as I got there with my graph values. So 2 ways to calculate K for a first order reaction. So that's concentration time graphs done. Okay, so I'm just going to ask how people are, or is everyone okay to keep going? Are we all right? Everybody happy? So I'd love to get today, I would love to get out of the way the rate concentration graphs, which is the next little bit. Little bit about clock reactions, which is again more sort of practical, sort of required practical side of things. And then there's the whole business of reaction mechanisms. Yeah, you can use either in an exam question. SAFC 1812, you can use either of those methods in an exam question. Okay, right, good. Thanks for that. Let's crack on then. So we're switching now. We're looking at a different type of graph now. We're not looking at concentration time graphs anymore. We're looking at rate concentration graphs. Okay, so remember that the rate of a reaction can be determined at any point on a concentration time graph. So we've just demonstrated that by calculating the gradient at that point. So if you do that multiple times, what you can then plot is another type of graph called a rate concentration graph. I very much doubt you would get asked to do this in an exam because it's too time consuming and it's not really worth, it's not demonstrating enough for the time it takes. It's not demonstrating enough or it's not testing you enough for the time it would take. So these don't really get asked. They tend to present you with the graphs and ask you about them. Okay. So what we've got here are the 3 rate concentration graphs. Okay. So the first one, again, I've not been very original at all with how I've set them out. This is your 0 order rate concentration graph. Okay, so basically what can we say? The rate is staying the same. It's got this constant value, whatever that is there. It's got this constant value. Concentration's changing, but the rate's just stuck at that value there. So that's how we can say from the graph that it's zero order. So how would you say that sort of technically? Rate unchanged or unaffected. Unchanged, is unchanged even a word? Not changed, you could say, by changing concentration. Okie doke. Next graph is for a first order reaction. Okay, so what have we got here? We have got direct proportionality between the concentration and the rate, and that's given us this straight line graph through the origin. So I'm just going to highlight that because that's really important. Obviously, if the concentration is zero, then the rate would be zero as well. Okay, if the rate depends on the concentration, therefore if the concentration was zero, the rate will be zero. So this graph has to pass through the origin. Okay, so let's write that in. So this is the rate is directly proportional, let's put prop, to the concentration. So if you double the concentration, you double the rate. If you treble the concentration, you treble the rate, and so on. Okay, that's what we looked at on Wednesday, but obviously this is the graphical representation of that. This is obviously a second order reaction. Again, it's important that it passes through the origin, because obviously if the concentration is affecting the rate, then when the concentration was zero, the rate would be zero as well. So that's got to pass through the origin. So the rate is proportional to the concentration squared, or the change in concentration squared. You could say, change that, change in concentration. Let's put a delta. Okay. It's the concentration time graph you don't need to know. You need to know all of these. You need to know these three profiles of graphs. Okay, so rate, concentration, you need to know all three. Basically, if I didn't include that in my notes with my students, somebody would say, what would the second order one look like? So rather than sort of go, you know, leave it to chance, I'm just going to say, well, you don't need to know that, but there it is if you're interested. Okay. The trouble is with, sorry, I'm going to go on a slight tangent here. The trouble with the syllabus, right? If it's not in the syllabus, they can still ask you stuff, because what they would say is, suggest the shape of the graph. You know, use your chemistry brain to predict the shape of this graph. Give a reason for your answer. Those questions exist, okay? So it's not on the specification sort of spelt out, but, you know, unfortunately, you could be asked pretty much anything. You know, and those types of questions are the ones that kind of differentiate between the A* grades and the A grades. You know, those students that can kind of come up with an answer on the spot. You know, you throw in this question about chemistry that you probably haven't been taught because it's not on the syllabus. You might still have to come up with a reasoned explanation. Okay, and that's your kind of harder A* style questions. So I would still, you know, I would look out for things that aren't on the syllabus and try and get your head around them just in case it comes up if you're interested in A*. Okay, right. Okay, So how would we calculate the rate constant K from a rate concentration graph? Right, so zero order first of all. So zero order, so I'll just write out the full rate equation. So rate, if it was zero order, rate equals K, say x to the power 0, yep. So therefore, that just doesn't need to be in there, does it? Because a to the power 0 or x to the power 0 is just 1. So rate equals K. So therefore, how would you calculate the rate constant from a graph like this? Well, K is just the rate, and the rate's constant, isn't it? So it's that value there. Okay? So therefore, K equals the rate, and I'll just say C graph above. Okay? First order reaction. So how would you calculate the rate? Sorry, the rate constant. So first order reaction, rate equals K, concentration, we'll say, of x raised to the power 1. Therefore, K equals rate divided by concentration of x. Therefore, i.e., it's the gradient. Okay, so straight line graph. So the change in rate over the change in x is the gradient. That's going to be your K value. Okay, so i.e. the gradient. So I think I've got on this one a value for K. So I'll just show you how I got it. I'm just reading off my notes here. Can I use that? Did I do it there? Yeah, 0.32, and I read along, that was it. Yes, that's not bad. So K equals 0.002 divided by 0.32, 6.25 times 10 to the minus 3 seconds to the minus 1. Okay, so the last one, and I've actually saying in the notes there, this is definitely not on the specification, the OCR specification. I have kind of explained how you would do it, and I have made a video on this, so if you wanted to check that out, please do so, okay? But I'll be very, very surprised if something like that came up on an exam as one of those suggest type questions. Some things you kind of think, yeah, I'm not surprised they've asked that, whereas something like this, nah, I don't think they would ask something like that. Okay, how we're doing for time? 3:50. Just looking at the notes, because yeah. So it looks like we've got, I think this is going to have to roll over into next week, I'm afraid, next Wednesday, and we'll be doing the mechanisms, reaction mechanisms, which is quite a sort of a bit to get your head around, and then we'll do the Arrhenius graph, and then that'll be that'll be everything. Okay, so I pretty much knew that it would take more than 2 hours to do this. Okay, when I teach rates of reaction in college, it is quite a big topic. Okay, so to try and do it in 2 hours is probably pushing it, and I think we can see that it's the case now. So we'll make this the last thing we do today, if that's okay. Right, so initial rate and clock reactions now. We'll finish with this. Right, so what we're saying here, remember that the initial rate is the rate at the very, very start of a reaction, i.e. at t equal to 0. The initial rate can be determined from a concentration time graph by calculating the gradient of the tangent to the curve at this point. Right, so let's draw a tangent. Okay, so that's okay. And how would you calculate the rate? It's the change in y. Whoa, oh, I'm in the wrong thing here, sorry. Change in y divided by the change in x. So the initial rate is the change in y over the change in x. So how do we I'll just throw a question into the chat, and then I'll just keep going, because there is a massive delay on this. Just wondering if anybody's done a clock reaction where you mix chemicals together, set your timer, wait until a colour change. I'll just leave that question hanging there. So a convenient way to establish. That's good to hear, thanks. I'm kind of, when I've been teaching this on YouTube the last couple of lessons, I've been thinking, I don't know how I would feel if I was a student watching this. How much would it actually make sense as a student? So that's good to hear. Thanks for that. So a convenient way to establish the initial rate is to perform a clock reaction. So in such, yeah, until you can't see the x, yeah, that's right. So you've done one, Alexander, yeah? A convenient way to establish initial rate, sorry, I've already said this, is to perform a clock reaction. In such reactions, the time is taken from the start of the reaction until a visible change occurs, and that's used to measure the initial rate. Yeah, disappear and cross with sulfur. Yeah, that's one. I don't do that one. I used to. It absolutely stinks, and I can't stand the smell. And when the students leave the lab, I'm stuck in this really smelly lab, and I don't like it. So I found a better one. Thank you, Laura. That's lovely to hear as well. Thank you. So it seems to be working, so that's good. Right. I can't face reading all this again, so where am I up to? A visible change has occurred. So it could be the disappear and cross, or it could be, the one I use is the reaction just goes blue like that, you know, over a certain amount of time. The average rate over the time period it takes for this change to happen is used as an approximation for the initial rate. So that's important. This is just an approximation, okay? The initial rate can therefore be expressed as 1 over t, 1 over time, and therefore would have the unit seconds to the minus 1. Okay, so a little bit about the limitations of clock reactions. And when I do clock reactions, you normally find that once you start getting to low concentrations of your reactant, obviously the time period's longer. When you draw the graph of your results, that's where the dodgy part of your graph is, if that makes sense. That's where your anomalous kind of part of the graph looks. The outliers tend to be at the high concentrations. And hopefully I'll try and explain this as clear as I can. Right. So we've got 3 graphs, okay? So let's imagine we're changing the concentration of reactant A. Okay, so you can see in the y-axis, sorry, concentration A, and what they've done is they've got a high concentration of A, yep, and this time period here is how long it's taken for the colour change to occur, or the cross to disappear, if that's the way you've done it. Okay, so obviously because the concentration is high, the time's quite short, because there's lots of collisions per second. Okay, right. So then you do your next concentration. So if you notice, that was your starting concentration. That's now your lower concentration. So you can see the time period has got longer because the concentration is lower. There's fewer particles, per unit volume, colliding per second, so therefore there's fewer successful collisions per second. And then obviously this is a lower concentration again, and it's taking quite a while for the change to occur. So I hope those three graphs so far make sense. Okay, so high concentration doesn't take long for the colour change, lower concentration takes a bit longer, low concentration takes quite a long time. Right, so that's kind of that first bullet, that first sentence there. Now this dashed line here. So the dashed line is a measure of the average rate over the time period for the colour change to occur. Okay, so this is the average rate. And what this is going to be used, this is going to be our measure of the initial rate. Okay, so as you can see in the high concentration example, the average rate for the time period, this one here, pretty much matches the gradient, the almost straight part of that curve there. Okay, so as you can see, the rate hardly changes for the shortest time, the highest concentration. So that is a pretty decent approximation of the rate of the reaction for that high concentration. Okay, and that's because the curve is fairly straight, so the rate is fairly constant in that short time period. Really hope this is making sense. Right, as the time gets longer, the average rate over that time period, that's what we're using as our measure of initial rate. But look at the curve, the gradient's changing. Okay, so that's not as good, that's not as accurate a measure of the initial rate, because the rate is changing ever so slightly over the course of that time period. Okay, so you can see there, as time increases, the rate changes more and more over the time period. For the long time period, that's going to be the measure of the initial rate of the reaction, but you can see the rate's changing quite a lot in that time period, so that is not the best measure of the initial rate. That's fine, absolutely fine, because it's pretty constant. Okay, now when obviously I can't see your faces now, but when I do that in class, I'm often faced with let's say a class of 25 students, you'll have about 5 students who are looking reasonably happy at this point, and then you've got 20 faces going, oh, I don't really get this. Okay, so I'm not sure if that was a good way to explain it, but I've tweaked the notes since last time I taught this, so these are the bang up to the minute notes, and this is as clear as I think I can make it, I'm afraid. You might want to retract your statement, Laura, that I'm making A-level easy to understand. I might have just cancelled that out. You jinxed yourself there. Okay. Right. So, last thing, I know it's 4 o'clock, but we may as well finish this section. So if you, let's imagine you performed a series of clock reactions, which it sounds like some of you have with your disappearing sulfur cross. A series of clock reactions were carried out for the reaction between hydrogen peroxide and iodine in acid solution. The presence of starch indicator enabled the production of the blue-black complex, blah, blah, blah. Okay, 5 experiments were carried out at the same temperature using a different initial concentration of hydrogen peroxide. Throughout, the concentrations of all the other reactants are kept the same. That's really important. Otherwise, if other reactants are changing their concentration, they could potentially be altering the rate because there mightn't be zero order. Okay, so to cut a long story short, there's your concentrations, there's your times. Okay, so what we're going to do is, it's asking us to calculate 1 over t for each experiment. 1 over t. So 1 over t is a measure of the rate. Okay, or I should say initial rate. Let's change that to initial rate. Well, Jake, I hope I haven't confused you. So I bet your teachers did a great job before lockdown. I hope I haven't just confused you with my way of explaining it. Be nice to hear that your teachers did a pretty similar job to me, but maybe I don't want to know the answer. Okay, so calculate 1 over t, in other words, the initial rate for each experiment, and plot a graph of 1 over t against the concentration. Include 0, 0 as a fixed point. All right, so effectively, what we're drawing 1 over t against concentration, what are we drawing? We're drawing a rate concentration graph. Okay, so that's what we're drawing, a rate concentration graph. So if I then go to the one that I've drawn, that's it there. Okay, so you'll see we've got concentration of hydrogen peroxide along the bottom, moles per decimeter cubed, so don't forget labels and units. 1 over t times 10 to the minus 2 I've got there. Let's just go back to this. Yeah, so I've turned these all into 1 over t's, and I've kind of done it times 10 to the minus 2. Sorry that when it's scanned in, it's just missed off that 10 to the minus 2. You might just be able to see it there. Anyway, what's it generated? It's generated a straight line graph through the origin. So we had to include that 0, 0 as a fixed point. Why am I doing 1 over t and not t? Because the question says plot 1 over t against concentration, because 1 over t is a measure of the rate. Okay? So this is a rate concentration graph. Rate concentration. So if you remember the three rate concentration graphs, we had that one, and we had that one, yeah, a curved one. So it's obviously this one we've got here. Yeah. So basically, by drawing the graph, we've established that this is first order with respect. Oh, Jake, yeah, that's good to hear for me. Thank you. Sorry, yeah, 2 hours of chemistry is a bit much, isn't it? Oh well, I'm pleased it's clear, because I do worry sometimes that I'm confusing people. Right, so I'll tell you what I'll do just to help you. If you're going to draw this graph, I got for my 1 over t, I'll just squeeze the values in here. I've got 0.043, 0.034. You may as well have these, I've already worked them out. 0.026, 0.015, 0.0078. Okay, and that's what I've plotted. So I've plotted that against that, and remember that is the rate. Okay, so it's a rate concentration graph. So use your graph to determine the order of reaction with respect to hydrogen peroxide. It's first order with respect to H2O2. How do we know? It's a straight line graph. Through the origin. Therefore, there's direct proportionality between the concentration of H2O2 and the rate. Yep, this is a required practical. You would have to be able to describe this kind of a reaction, okay? Right. Okay, I'm gonna sit back on my sofa now because I am done. I'm done in as well. I don't know about you, but it's been a long week. So there. Has anybody got any questions on what we've done this afternoon? If not, I will wish you a good weekend, and we will pick this up on Wednesday. So we've got rate determinant step and prediction of mechanisms, which is a great topic, and then we've got the Arrhenius graphs. Feel free to check out my videos on this in the meantime, because I've obviously made everything already, so you might want to watch those, and then this could be a revision session on Wednesday rather than being taught it for the first time. That's definitely directed at my students, that, by the way. Okay, nudge nudge. No questions? Just reading that message there, Jake. Thanks for that. Notes are only quite concise. I'll take that. You've said clear. You're welcome, Rebecca. Maybe watch the videos on mechanisms, rate determinant step and mechanisms before Wednesday, and then, because I've already posted the links to you, so if you watch those beforehand, then hopefully Wednesday will make loads of sense, loads more sense. Okay, yep, see you next week. Okay, and then before you go, I'm thinking of doing benzene after this. So we'll do rates and then we'll do benzene. I fancy doing some organic chemistry for a change. So we'll just mix and match. And then I need to decide what I'm going to do over the summer holidays. Do I still do live streams over the summer holidays, or do I have a break? Haven't decided yet. Okay. Right, fantastic. It doesn't seem to have your students. I've kind of decided for them, Jake. We're going to do benzene. We're going to do aromatic chemistry. Going to switch over to organic, which is normally the topic I would do. Oh, it's a bit late now, Jake. The damage is done. Damage is done. Jake, in terms of topics, what were you thinking you would like? And I'll see if I can weave that in maybe the week after, if you're still there. Not sure if you've gone yet. Not done benzene yet. Well, won't do you any harm to see it, and then when your teachers go through it in college, when you get back after the summer, you can be sitting there all smug because you've already done it, if you fancy. Okay, might as well come along. Feel like you're part of the class now, part of the group, as is everybody else. Okay. Right. it's all gone quiet, so I think I'm going to say goodbye. Okay, right, have a great weekend everybody, and I will see you on Wednesday, and I promise we'll finish rates on Wednesday. Okay, so 3 sessions on rates, which is quite understandable. Okay, you've done carbonyls before benzene. Okay, right. Well, we can look at carbonyl compounds in another live if you want. That's fine. I'm probably going to keep doing these over the summer, I've decided. Otherwise I'll get bored. If I'm not going on holiday, I might as well do something. Yep. Acids and bases. Oh, that's another big topic. Yeah. But yeah, Laura could do that as well. That's absolutely fine. Cool. Okay. Right. See you later. Bye. Just going to wave. Bye. And then everybody needs to go. Haven't done benzene yet. Okay.